So I think we can start. So it is my distinct pleasure to welcome you to the EURASIP webinar organized by the European Association for Signal Processing. So today we are featuring a talk by Tirza Routtenberg from Ben Gurion University in Israel. My name is Marius Pesavento. I'm sharing this session today. And just briefly, Professor Tirza Routtenberg received her bachelor degree from Technion University, the master and PhD degrees from Ben Gurion University. She was a postdoctoral fellow at Cornell University before she joined Ben Gurion University as a faculty member, where she's now an associate professor. And most recently, she has been a visiting professor at Princeton. Her research interests include statistical signal processing, graph signal processing, as well as optimization and signal processing for smart grids. And yeah, of course, this is also the subject of today's talk. So I welcome you, Tirza, and yes, thank you for being here in these, of course, difficult times.
Thank you very much, Marius. Thank you for the kind introduction and for the invitation. So again, I'm Tirza Routtenberg from Ben Gurion University, and today's talk is about statistical graph signal processing with applications to power systems. Because this is a webinar, you have the QA sessions that you can ask by the chat questions, and Marius will handle that. So please feel free to ask during the talk or after the talk. You have also here my email if you want to email me after the talk. Okay, so does it work? It doesn't. Oh, no. Okay. So the overview for today, and I guess we are not going to see everything, but part of it. So I will start with some background and motivation for the problem of graph signal processing, statistical graph signal processing. What do we want to do? Then I will present the state estimation problem in unobservable power systems. So most of the talk today will be about state estimation problem. We will see different methods for different types and settings. And I hope I will have time to mention also some other topics such as topology identification and so on, and the conclusion. So why graph signal processing? So if you think about that, around us, we have various networks. We have virtual networks like the social network, when we have some entities and some connections between them that we can model as a graph, as a mathematical graph with vertices and edges. We have physical network or even infrastructure networks like the transportation network. Here you can see Manhattan transportation network. The electrical networks, when we have some transmission lines and they can be represented as a graph. You can think about the brain network or other biological networks. And all these networks can be represented as graphs. Once we have these graphs, we want to process the signals, the data, the measurements that we have over these graphs. So we consider that we have different data from these people, for example, in the social network or in the power systems or electrical networks, we have some measurements of the voltages, of the power, and things like that. These are the signals, the graph signals that we want to process, okay? So graph signal processing is actually signal processing with a structure of a graph. And since graph signal processing is based on networks, which are all around us, this is a emerging field, and you can see here. So of course, we have the traditional graph theory from 100 years ago, but we also have the field of graph signal processing, which is built upon the graph theory, which is basically started 10 years ago. Okay, you can see here some of the famous state-of-the-art papers in this field. And GSP theory, the idea is to extend concepts from traditional digital signal processing, DSP, to the graph domain, to the irregular graph domain, which is not so simple. We will see that. So for example, sampling and recovery, filtering. We have also graph Fourier transform that we are going to see today, convolution, denoising. So all these concepts, but now they are going to work on graph signals with this irregular structure. Okay. Now, the goal of our work today, the work that we are going to see today, is to extend the statistical signal processing. So most of the GSP theory, at least at the beginning, was about deterministic signals and without the statistics. So we are going to extend not just the DSP to GSP, but also the SSP, the statistical signal processing, which includes, for example, estimation theory, detection theory, anomaly detection, blind source separation, and so on and so forth. The talk today will focus on estimation theory, but we also have works on all the other topics. So why power system? Why electrical grids? And we like to call it GSP for PSG, graph signal processing in power system grids. So power system or electrical networks for us, this is the same, okay? So you can think about electrical networks. So here you can see a diagram of an IEEE test case, the 30 bus test case. You can see here transmission lines, you can see here loads, generators. So it's very natural to represent it as a graph here in the right, okay? This is the same representation of the same system, but in the right, we see it as a mathematical graph with some nodes and edges, okay? You can also see the signal. This is the colors here. These are the voltage angles. This is the signal that we measure here or we try to obtain. So naturally, if you think about that, graph theory started with electrical circuits, okay, with Kirchhoff and Ohm and all this theory. So it just makes sense to use graph signal processing tools for power system applications, for electrical networks. So our first motivation was how to use GSP tools to solve problems in PSG. But then we realized that it works also the other way around. So we can use the power system as a motivation, as an inspiration for recognizing what are the important problems that involve graph signals. And then we want to develop new GSP tools that can be used for any application. So even if you are not interested at all in the power system and electrical networks, I hope you will find it useful, what we are going to see today, because it is not limited to the power system. Okay, this is a conventional state estimation problem over graphs. The inspiration is coming from the electrical networks. Okay, so let's see some definitions, and I will try to keep the mathematical aspects not too long, but there are some definitions that we need. So in this talk, we are going to consider undirected, connected, weighted graph. Okay, so all the graphs that you are going to see today are undirected, they are weighted and connected. V is the set of vertices. I'm going to use vertices and nodes equivalently. Okay, there is no difference between them for us. Along the top, the number of nodes is n, okay? And the number of edges is m. So C is the set of edges. Again, these notations are for all the parts, all parts of the top. We assume that the edges can have some weights, positive weights, okay? So the edge ij, which is in C, has the weight wij. If there is no connection between two edges, we will say that we have zero weight. And we can define various algebraic operators or matrices that represent the graph. In this talk, we are going to focus on the Laplacian matrix. If you are familiar with GSP theory, then you know that I can use also other matrices. So it is not restricted to the Laplacian. It is the easier way to represent the concepts. And the Laplacian is a very nice matrix. So this is the reason that we are going to work with it. But you can use other matrices that represent the graph. The name is graph shift operator. So any matrix which is a graph shift operator can be used for our theory. So the Laplacian, the off-diagonal elements of the Laplacian matrix is the weight with the minus sign. The diagonal element is just the sum of all the weights that are going into a specific node. Okay, so here you have an example. 2 and 3 are disconnected, so I have 0 weight. 3 and 1 are connected, so I have -4 and so on. Okay, so this is the Laplacian. This is the main player of this talk. The second main player is the graph signal. The graph signal is just a vector. This is a vector that is associated with the nodes of the graph. So we have scalar value. X1 is associated with vertex 1. Okay, so we have n-dimensional vector. So you may ask, okay, this is a vector. What makes it a graph signal? I am going to try to convince you that there is some meaning for this graph signal definition, but basically this is a vector. So the first definition is that this is a vector with the same dimension of the vertices. Of course, again, you can extend it to multi-time, and then it won't be just a vector, but a set of vectors, and I have different measurements for each time of these specific nodes and so on. But again, we will try to keep it simple. So for now, this is a vector. Okay, so the first thing that is associated with the graph signal is the variation, is a measure of variation over the graph. And this is the graph signal variation, which is defined here. Again, we have two main players, the graph signal and the Laplacian. So we have here X transpose Lx. This is exactly the scalar value that is obtained by their multiplication. And it can be shown that this is, it equals to the weight, Wij, the weight of specific edge, multiplied by the gap between the values of the signal Xi and Xj at the two endpoints of this edge, okay? And this sum is only over the connected edges, okay? So you can look here in the figure, in the left one, all the signals are the same. This is a constant vector, so I would get variation of 0, which makes sense. But here I have different values for each nodes, and then the variation is higher, okay? So this is a variation with respect to the graph, because I measure the variation only for connected nodes and between the values at the ends. It has different names, total variation in some cases. You can use other norms, not just the second one, and so on. And it is 0 only for a constant signal. So again, measure of variation. It was used from the 90s in image processing as a regularization for image processing. So by applying that the GSV should be smaller than a value, you can recover images that are smooth, okay, that there is no many changes in the figure. Okay, so now we want to use this regularization for a problem that arises from the power system, but again, you can use it for other applications. What you see here is a linear model, okay? It is, the name in power system is DC power flow, but this is not a DC power. This is a linearized model. What you have here is a noise plus linear term. We don't know theta, and we want to estimate theta. Theta, in this case, is the system state vector. In this case, theta n is the voltage angle at pass n. Z is the vector of power, so I have different length of this vector. H is a known matrix. This is a matrix that represents a graph or the network. It is based on its topology, on transmission line properties, meta locations, and so on. And we have a submatrix of this matrix H, which is a Laplacian matrix. This is the nodal admittance matrix. So we have here a connection between the mathematical aspect and the physical aspect. Okay. So I will answer, I will stop in a few minutes, and then I will answer the question in the chat. Okay, so, okay. So our goal is to estimate the states from the power data, but as you can see here, I don't have the full vector Z. I only have sub-vector with this notation S. This is the set of observed sensors, which is small, meaning that we have unobservable system. It can be due to communication errors, topology changes, sensor failures, attacks, and so on. I don't have enough measurements. This is the situation, okay? And I still want to recover theta. So this is, again, a well-known problem from signal processing. This is ill-defined problem. And we cannot do that, yeah? We cannot estimate theta if I don't have enough measurements. So I need an extra information. The extra information comes from the graph signal processing. So we are going to use the fact that the graph signal variation, the smoothness of the states theta, is small. So it is that the states theta has a small variation, okay, or small GSV. Okay. In order to do that, I need to convince you that this is the case. So we tested it, and that's, again, this is a new result from the last years. It's not a well-known result. So we tested the theta vector, the vector of the states, and the measurements, okay, so voltages and power, for different IEEE test cases. This is the typical test cases of IEEE of electrical networks, and the number 14 bars, meaning that we have 14 nodes, 30 bars, 30 nodes. So what you can see here is that if we compare the GSV of theta and GSV of Z, obviously we can say that theta is smooth, has small GSV. It is the normalized GSV, but this is the GSV, and that the power is not smooth. Okay, so we have a physical property. We cannot just incorporate extra information that we imagine. We should check that. So that's what we did here. In order to use this tool, we first established the fact that theta is smooth. And then we realized, okay, we need to have a methodological way to do that. And this is a recent paper that we submitted about how to verify the smoothness of graph signals. So this table is nice, but if you want algorithm, which is based on generalized likelihood ratio test and model-based approach, then this is the general approach of how to verify the smoothness of the small GSV of a specific application. So if you want to apply the approach that I'm going to present now, you should first check that in your application, the graph signals are smooth, because again, the power signal is also a graph signal, but it is not smooth. It is not. It doesn't have a small GSV, but theta, the states, is small. Okay, so then that's the main idea. So the GSP weighted least square, okay, is just what you see here. This is the minimization problem. We have here the first term, which is based on the data that we have. This is the measurements over the set of sensors S, and we have this regularization term, which is based on the smoothness. Okay, now let me see the question. So the question in the chat is, what are the origins of the concept of total variation in graph signals? Is graph signal variation have any relationship with Rayleigh quotients? Yeah, I'm going to, we are going to see that in the, let's say in 5 slides, okay? I will say about that a few things, okay? So you still need to wait for a few 5 slides, let's say. Okay, so now that we have this optimization, and gamma is just controls the relative importance, and of course it cannot be too large, because then the solution will be 0, and it is based, the value of gamma should be based on testing and also on the eigenvalues of the matrix H. Okay. Marius, oh, I see it works. Okay, so the solution is what you see here. This is the estimator GSP weighted least square. It has a K matrix multiplied by the measurements. This is the K matrix we have here. This is our regular terms. We have this regularization, which is based on our Laplacian matrix. Now, we also wanted to extend it. Usually in power system, people work with the nonlinear model. In this case, we have these measurements. The measurement function is not linear, but is known. And because it is not a convex problem at all, it is solved by iteration, usually by regularized Gauss-Newton methods, but it can be with other methods. So in this case, we also added this regularization, but at each step of at each iteration of the algorithm. Okay, and in this case, we estimate both the voltage phases and voltage amplitude, so we have a longer vector. So then we ask ourselves, okay, the sensor locations have a significant impact on the estimation. Maybe we can optimize them. So we wanted to optimize them in terms of the estimation error. But if we try to optimize directly the MSE of our estimator, the new estimator GSP weighted least square, then it is a function of the specific theta, which is impractical because, again, the states is different. I'm now implementing this estimation, and this is a very important problem in power system. It is done per hour and even per minute. It depends where and depends what are the applications, but it is a real-time problem. We have different theta, different states for each time. We are not going to put the sensors for each specific theta. We need a general solution that can be used for each system, and we are not going to change the locations of the sensor. Okay. So instead of that, we suggested to use the Kramer-Rao bound. The Kramer-Rao bound is a lower bound on the MSE. And this is the term that you see here, is the biased CRB, which is associated with our estimator. Okay, so we know that we are going to use this estimator, the GSP weighted least square. So we are we are trying to optimize the Kramer-Rao bound. Okay, and because this is a combinatorial optimization, because we need to find all the locations of each sensor, and we have different combinations of sensors, we are using in practice a greedy algorithm that iteratively adds buses or nodes with the minimal Kramer-Rao bound. Okay, so we have till now we have estimator and we have a bound. Let's see some results. Okay, so what you see here, again, this is for the application of state estimation in power systems. We compare three estimators. The first one is the conventional that is used in power system. This is the pseudo measurements weighted this way. The pseudo measurements in terms of signal processing is the Bayesian estimator, where if I don't have measurement, I'm going to assume that this is a Gaussian with a zero mean, okay, with some variance. Okay, so this is a pseudo measurements or virtual measurements. The matrix compilation is a sparsity-based method. So this is assumed that we have some sparsity of the states that we are trying to estimate and our estimator. I'm going to compare between sampling policies, random sampling policy, eDesign, which is a new GSP tool. You see from the year, this is a GSP tool that is associated with graphs, and our CRB-based algorithm. And I'm going to implement it on the 118 bus system. Okay, so you see here the MSE versus the measured buses. Okay, so of course, if I have full knowledge of all the buses, 180 buses, then all the estimators perform the same. But if I don't have enough sensors, in this case, you can see that our estimator together with our sampling policy, so GSP weighted least square together with algorithm one, outperforms all the other methods. But also you can see here that our estimator also works well with other sampling policies, and that our sampling policy also improves the performance of the other estimators. So the take-home message from this point is that we can improve if we know physically that we have a signal with small variation, then we can improve by regularization the estimation, and we can also design a sampling scheme which is associated specifically with the task of the estimation. So the eDesign is not specifically for the task of estimation, so it is good for general graphs, but this is specifically for the task of estimation, the CRB-based algorithm. Okay, so now I'm going to answer to the question in the chat. Sorry for waiting so long. So till now what we saw is just the variation, okay? But we want to have something more than just a scalar value. So then we want to look on the eigenvalue decomposition of the Laplacian, okay? So if we look on the eigenvalue decomposition of the Laplacian, we have the matrix V, we have the matrix lambda. V is the matrix of eigenvectors, lambda is the diagonal matrix where lambda n is the nth eigenvalue, okay, associated with Vn, the eigenvector. And then I can define graph Fourier transform. And for now, this is just a definition. X tilde equals to V transpose X. So again, my player, the Laplacian, again, you can extend it to other matrices, determines the GFT, the graph Fourier transform, because I'm using its eigenvalue matrix. Again, of course, the inverse GFT is just multiplication by V, so we can going back to X. So again, X tilde, from now on, the tilde are in the graph frequency domain. So then you may ask, okay, I can take different matrices and I can define different transformations. Why do I call it graph Fourier transform? Why this is the case? So then from the Rayleigh quotient, as commented in the Q&A, we have that the smallest eigenvector, okay, that is associated with the smallest eigenvalue, is the eigenvector that minimizes exactly the GSV, X transpose LX. This is the eigenvector of L, okay? And from this mathematical formulation, we know that the smallest eigenvector is a constant vector. And then I will obtain a zero GSV. There is no variation for a constant vector, okay? So this is the smallest eigenvector, the eigenvector that is associated with the smallest eigenvalue. But then if I want to go from the Rayleigh quotient, if I want to have other eigenvectors, then I'm continuing with minimizing the GSV, exactly X transpose LX. I just need it to be orthogonal to the previous eigenvectors, okay? So what does it mean? It means that the Laplacian eigenvectors are ordered by their increasing variation, okay? So we have a new notion of variation, okay? The variation is measured by the eigenvalues. These are now our graph frequencies. The graph frequencies are the lambda, okay? Where the dictionary elements are the columns of the matrix V, okay? And here is a very nice picture from Ortega's paper about, this is an illustration of a specific graph with the different eigenvectors. So here you can see that this is the smallest eigenvector. This is a constant vector, associated with lambda equals 0. And then if I'm going to the second smallest eigenvalue, then I can see that, okay, there is a variation, but I can pretty much divide it to two areas where there is no much variation in each area. Then I'm going and increasing the variability, which increases with the lambda value. Okay, so now I have a new notion of graph Fourier transform. Okay, I have graph frequencies. These are the lambdas, and I can represent my vectors based on their variation with respect to our graph. Okay, so this is the main idea. So now, as a signal processing people, if we hear about graph Fourier transform, then we say, oh, we want to do filtering. Okay, so this is exactly what we can do. So if we look on the frequency domain, we can take our signal, compute the graph Fourier transform, just multiplication by the eigenvector matrix with transpose. And then we take a diagonal matrix that do the filtering. So we have like, it can increases some values that associated with some graph frequencies, it can decreases and things like that. So I think, for example, if you want to have high pass filter, then in this case, you can detect some anomalies. We did it in some of our papers. So you try to increase the high pass filter, so the high values of the lambdas, okay, of the eigenvalues of the Laplacian. And then I can compute the inverse graph Fourier transform to going back to the graph domain, to the vertex domain. This is very nice, but as we know from DSP, we also can define the filtering in the time domain, okay, in conventional DSP. For example, if you think about moving average, we are averaging over different time domain samples. So here we are doing the same, but now we take averaging over neighbors, okay? So this filtering approach is vertex localization, y equal to this matrix multiplied by x, where this matrix is a polynomial in L, that you can see here, okay? So for example, if this polynomial has the order k, it means that I'm going to average over k hop neighbors. So no longer distance than k edges that are connected between the nodes that are going to impact the value here in red of the signal in the node red. Okay, and if you are coming from learning theory, so this is exactly the convolutional kernel with a graph shift operator, again, not necessarily here. So what is nice is that exactly as in DSP, these definitions of graph filters are equivalent. So you can work in the frequency domain, you can work in the vertex domain, you have this relation between them, linear relation between them. So it's not that simple, but it is close to be simple. It's like in DSP, we can find a connection. If you want to design specific filter design, you can work in the vertex domain. Okay, but in this talk, I'm going to focus on the frequency interpretation, but just remember that you can work also in the local domain. So from now on, graph filter is this diagonal matrix, okay, and the multiplication with the V, okay, this is exactly the graph filter that we are going to see from now on. Okay, good time to see questions. Reason about unnormalized Laplacian is used instead of normalized as a Fourier basis. There are some reasons for that. I don't think that I'm going to go into that now, but just I think it is important to say that here it is normalized. So here I'm going to take only eigenvectors that are has unit norm. Okay, but this is a good question about the normalization. You can also normalize because, as I said, maybe I will answer this question. The Laplacian is only one choice. You can also take normalized Laplacian, and it has different names, the normalized Laplacian. Or you can take the adjacency matrix or the weight matrix. In this case, you will get different eigenvectors and eigenvalues. Okay, and a great question is how to choose this basis, how to choose this matrix that represent the graph. Okay. Okay, so let's move to the main part of this presentation. This is the Bayesian estimation of graph signals. And the problem is pretty simple. This is the problem that I'm going to focus for now. We have a very simple problem. In some communities, the name of this problem is inverse problem. In some communities, this is estimation of a vector or multi-parameter estimation. In some cases, this is a recovery, signal recovery. Okay, so we have different names for this problem. But at the end, we have measurements, y, Okay, we have some measurement function G, which can be function of our topology via the Laplacian matrix L. It can be also a function, it has to be a function of X of our unknown graph signal, and I have some noise. Okay, so I have, again, graph signal, meaning it means that it is an n-dimensional vector. Okay, you can assume that you know the probability density function, the PDF of this X. Okay, this is random vector, so this is the reason for the title Bayesian estimation. We are trying to estimate random vector. We assume for now that L is non-Laplacian matrix and we want to recover X. The only problem is that this function is highly nonlinear and we want to have a low complexity or at least practical recovery of X from Y that we can implement. Okay. As an inspiration, the motivation came from state estimation in power flow, the problem that we saw before. It is highly nonlinear. I showed you the linearized version, but it is highly nonlinear, and it has been proved as NP-hard problem. Okay, so we know the function G because this function G came from Kirchhoff and Ohm laws, but we don't know how to recover X from Y. Okay. So then at this point, you may ask, okay, this is a conventional Bayesian estimation problem. What makes it a graph signal processing problem? Okay, X and Y has the dimension of n, but this is not exactly, this is not limited to graphs. So the answer in our context is that X is a graph signal. So we have here the notion of graph frequencies or the algebraic graph structure. We want to use L, our Laplacian, our structure, as side information, both for efficient computations and for representation, and we are going to show that it has many advantages. So that's my job to convince you that there is a difference, and this is not just a conventional Bayesian estimation. Okay, so let's remind ourselves what happens in conventional Bayesian estimation. So the optimal estimator in the sense of MSE, the minimum mean squared error estimator, is the conditional expectation. Okay, I'm trying to estimate X from Y. So this is the conditional expectation of X given Y, but this is intractable because G again is highly nonlinear. You don't know the probability density function of X given Y, the conditional PDF, and it does not have an analytical form. And if you want to use Monte Carlo or integration, this is also intractable because think about a large network, okay, where X and Y are multidimensionals, and they are highly related. There is no independency between them. Okay, so you have to do multiple integrations. This is impossible. Okay, in this context. So then you may suggest to use the linear MMSE. This is the estimator that minimizes the MSE among the subset of linear estimator. Okay, and this is the structure of the MMSE with covariance matrices between X and Y, covariance matrices between Y and itself, with the inverse sign. But again, you need here to know the second order statistics of X and Y. This is intractable as well. Okay, you cannot compute analytically these statistics. However, here you can do some Monte Carlo integration. And because, just as a reminder, we know this function G. Okay, so we can generate fake data with Y and X that satisfies this equation. Okay, if we know the noise characteristics, we can just have many data points of Y and X. Okay, this is doable. So what you can do is to use the sample LMMC estimator. So to replace these matrices with the sample mean version. So to replace the covariance matrix by the sample covariance matrix. What are the problems with this sample LMMC estimator? It requires extensive data set. So we want to evaluate this inverse of the matrix, and perhaps our system has changes all the time. So you cannot, it's not stationary. So you have problem with this generation of data. Also, you are not using here any information of the underlying graph. Okay, I know that this is a graph signal. I know the Laplacian head, and you are not using this, at least not explicitly. So it is going to be less robust to topology changes, for example. Think about, again, the electrical network. I can have some outage. I can have some disconnection, some switch that goes on and off. Okay, there is no straightforward methodology to update my estimator to this new topology. Okay, only a change of one line in a network with hundreds of nodes and my estimator doesn't work at all, okay, from now on, and it ignores the GSP properties. So our desired estimator should be based on small data sets, should be robust to perturbation of our topology of the graph, changes in the graph, should be adaptive to these changes. So we want to have a methodology to update this estimator and should be based on GSP property. So what we took at the beginning is just a graph filter. So we consider now that our estimator has this structure of graph filter. Again, V is the eigenvector matrix of the Laplacian, lambda is the eigenvalue diagonal matrix, and here f of lambda is our diagonal matrix. This is the filter, okay? So we only need to find this filter and the bias term. These are two vectors because the filter is a diagonal matrix and B is a vector, so it's just two vectors instead of finding matrices. And this is the subset of estimators that we are going to use. So of course, these are linear estimators and they are restricted. So potentially they can be, they can have lower MSE, higher MSE than the LMMSE. So they can be worse compared to the LMMSE. Okay, let's see why do we use this graph filter estimator. So we minimize this. This is the MSE term, okay, because here you have the estimation error. This is the MSE. We are minimizing it and obtain this GSP LMMSE estimator. Again, what you can see here is a filter. Our filter is composed of two diagonal matrices. D is diagonal for diagonal matrix. This is the covariance matrix between X tilde and Y tilde. So it's X and Y, but in the graph frequency domain, okay? And here you have the inverse of a diagonal matrix, okay? Again, V and V transpose are assumed to be known, okay? So this is the GSP LMMSE estimator. It is very similar to the structure of the LMMSE, but now I am going to be based only on diagonal covariance matrices, diagonal in the graph frequency domain. So this is the diagonal LMMSE estimator in the graph frequency domain. And of course, I don't have the statistics as well, also here. So I'm going to use the sample mean version. Okay, so the sampled GSP LMMSE. Okay. Now, what are the properties of our new estimator? So first of all, it gives insight into the frequency content of our nonlinear graph signals. Second, it requires the estimation of only two n-length vectors. And it is very easy to compute the inverse of a diagonal matrix. So it is non-singular with probability 1, even if I don't have enough data. And it has a reduced computational complexity. But this is, just to be honest here, it just if I have the eigenvalue decomposition of the Laplacian, okay? So under the assumption that V is given, then it has a reduced computational complexity. Now we want to find the situations where the GSP LMMSE coincides with the LMMSE estimator. So again, LMMSE is the optimal in the linear sense. Our estimator is not necessarily optimal because we restrict ourselves to the graph filters. So this is the condition in which the multiplications of the full covariance matrices equals to the diagonal case, the diagonal covariance matrices. Let's see when does it happen. So the first case, and this is, I think, very nice property because it relates the result to the communication theory. So if you take the case where the measurement function is separable in the graph frequency domain, and here is the definition, orthogonal frequencies. So our measurement function G tilde in the graph frequency domain is only function of this specific frequency. We have some orthogonality between the frequencies. In this case, our estimator is also the LMMSE estimator. And this is exactly, if you are familiar with communication OFDM systems, when you have orthogonal frequencies, okay, and you process the signals at each channel, at each frequency band separately, okay? So this is exactly the situation here, which is very nice. So this can be seen as an extension of the OFDM concept, okay? The second extension is if G is linear function and not just linear function, if this is a graph filter output, okay, and this is a very specific model, in this case, our estimator is reduced to the LMMSE, but also to the graphical winner filter, which has been proposed a few years ago. Again, this is in the context of GSP. So you can think about our estimator, our GSP LMMSE, as the extension of the graphical winner filter, but to the nonlinear case. So these are two nice special cases. But again, in the general case, this is important to understand. In the general case, we have a different estimator. This is the idea that we suggested a new one. This is just the optimality conditions. Okay, so then the only problem is that if you look on our estimator and on its frequency response, it is restricted to be defined only for our specific eigenvalues. And as I told you, we want to have a frequency response that can be used with different values of lambda. So for example, again, I have a new graph. Okay, I want to be able to adapt my frequency response of my estimator to the new graph. So we want to find our estimator among specific parameterization of our graph. What does it mean? So again, as in the DSP, we have here the autoregressive moving average graph filter suggested a few years ago. And this is a function of continuous lambda value. Okay, so you have here the polynomial term in the numerator and denominator. Okay, and we have a function of lambda, which is a continuous value. Okay, so now instead of finding this matrix, I want to find this frequency response. So I restrict my estimator to be with this specific filter, the ALMA filter in this case, okay, to has this frequency response. And I'm trying to find the best coefficients of the polynomial. These are the parameters of. Okay, so this is, again, it's the same estimate of the GSP LMMSE, but with the function h. What do I get? So you can see here in black circles, okay, this is the frequency response of our original estimate of GSP LMMSE, which has specific lambda n. It is only defined for the eigenvalues of our Laplacian that we started with, okay? But if we take the ALMA filter, and I only use 4 coefficients for each polynomial, okay? So it's like I only use 8 coefficients altogether. And you can see that I have a continuous frequency response now that I can use for my estimation. And you can see that it is very close to the original GSP LMMSE frequency response that is based on 180 nodes in this case, okay? So we have here a method for universal design of graph filters by fitting the graph frequency response over a continuous range of graph frequencies. So now you can give me any graph that you want. I can use my frequency response and implement it with the new graph, okay? What is nice is that I have a method which is adaptive to topology changes. So the original LMMSE estimator does not have a method for this adaptivity. It can reduce outliers, errors, and noise effects on the sample mean versions because I need to recover only fewer parameters. And we can also use some local implementations, local in the meaning of the graph, locally in the graph. Okay, so let's see some simulations. So I'm taking here again the problem of power systems. I have in the power system, the vertices are the buses, generators, or loads. The edges are the transmission lines between those buses. And the weights are the branch admittance, okay? I have the voltages X, but the data is the power. So usually people measure the power. Based on Kirchhoff and Ohm laws, we have this equation of the measurement equation G is what you see here. So I'm trying to recover X. You see this is a cosine of X, sine of X. This is highly nonlinear. So let's assume that I know this V, I know this G, I know this B, but still I need to recover X. This is NP-hard problem. Okay, and again, it is proved, not by us, but it is proved that this is NP-hard problem. Okay, so let's see, and we use test cases from IEEE. So what you can see here is the mean square error versus the number of data points. So we need to compute, we cannot use the statistics, so we need to use the sample covariance and sample means. So the data point that we have is XP and YP, and we have total of P points, okay? What you see here in black is what happens if you take P to infinity or to be very, very large. In this case, this black line represents the LMMSE, the optimal estimator, because asymptotically it should be achieved by infinity measurements. But in practice, we don't have infinity measurements. So what you can see here is that our GSP estimator, both versions, both the ARMA version and both the original one, have smaller MSE than the linear for a few data points. And again, this is a system with 180 nodes, okay? So the LMMSE, the sample LMMSE is okay, but it needs a lot of data, okay, to recover. And this is, again, this is a small network. Usually we have hundreds of classes of nodes. And our estimator converges much faster. And this is, it happens for different values of sigma. This is the same graph, but just versus 1 divided by the noise variance, just to see that this is constant. It's not for specific value of sigma that we took. This is, it happens for different values. Okay, and what is more important is that what happens if we have new edges or removed edges? In this case, as you can see, the linear estimator, the sample LMMC, does not work well, while our estimator has lower MSE. And here you can see, okay, here still, we also have larger MSE if we removed edges because of the stability issues, but we still constantly lower than the LMMC estimator. So we are more adaptive to these topology changes, okay? So then, I don't have much time. So for now, I will present some extensions, okay, of this concept. But the concept is similar, but for different situations and different scenarios, okay? The first extension is for complex value signals, because again, we got our inspiration from the power systems where we try to recover the voltages. The voltages are not just the angles, they have also the amplitudes, or if you want, they have the real and imaginary parts. So we try to recover complex value signals. So our goal now is estimating a graph signal X, which has complex values, where also the observation is a graph signal with complex values. I assume here 0 mean signals just for simplicity, but we do not assume that the signals are proper. So in general, they can be improper. Improper meaning that the covariance between Y and Y transpose, okay, transpose, not Hermite. So it's just a transpose without complex conjugate. This covariance matrix is not necessarily 0. This is improper complex value vectors. Widely linear estimators are in general, and not in the context of graph, are linear functions of the augmented vector of Y and Y complex conjugate. Okay, so there is here some redundancy in the information because we take Y and its complex conjugate, but still it has been shown that using this linear function of these two terms via the widely linear LMMC estimator significantly outperforms the linear estimator, the LMMC estimator, for improper random vectors. Okay, and it has also many desired properties. So this is our goal now, because widely linear estimator do not utilize the graph properties, and therefore they need large sample size, because again, we are going to use the sample mean versions, and they are not robust to changes in the graph topology. So the solution that we are presenting now is widely linear estimation methods for improper complex value graph signals. I'm not going to get into all the details and all the mathematical equations, but just conceptually, in the linear estimator before, we took a graph filter. Here we take two graph filters, one that filters Y and one that filters Y complex conjugate of Y, okay, to estimate X hat. So of course, two filters are better than one in this context, but let's say that. And if you want to see the big picture, so here you can see a figure of subset of estimators. Okay, so what we saw in the previous part is the GSP linear estimator, when we need to set two end parameters, the diagonal element of the covariance matrices. This is the sample matrices that we try to recover. Okay. There are the widely linear estimators for the general case, not the graph. Then you need to find 4 matrices of n square. Okay, this is pretty large. You need a lot of samples for that. You have the linear estimators when you only need 2 full matrices. And what we are going to do now is this gray area is the GSP widely linear estimator with 4 n parameters. So you can see the GSP widely linear estimator includes the GSP linear estimators, and but they are not included, or the opposite with the linear estimator. So we have this nice structure of these groups. Okay. So again, without equations, just to see some nice solutions. So of course, some theoretical results about our estimator. So of course, in the proper case, if this matrices, the covariance matrices between Y and X transpose, Y and Y transpose are zero, okay, we did not assume that, but if they are zero, then our new estimator GSP weighted LMMSE estimator is reduced to the original, the one that we saw in the previous part, the GSP LMMSE estimator, okay, because in the proper case, linear is the best. You don't need to use the wide linear concept. In the case where X is a real signal, okay, but Y has complex value, in this case, our new estimator, the GSP widely linear MMSE estimator is real, which makes sense. You are trying to estimate a real value, so it makes sense that your estimator has real value parameters. But if you use the linear estimators, both linear estimators, both our estimators and the previous, the conventional MMSE estimator, they, in general, they have complex values, which it is an absurd result, okay? Another nice property is that if you have a graph filter as your measurement function, but graph filtering of X with complex conjugate, then our estimator has zero estimation error, but the previous one, the linear estimators, in general, have a non-zero value. So these properties should convince you that it makes sense. If you have the improper case, then it makes sense to use the widely linear results. Okay, and we have also some extensions in the paper. So let's see some simulation results. And in this case, again, we are trying now to estimate the voltages X that includes their complex values. So they include both the real and imaginary part of the voltages. This is the Kirchhoff and Ohm laws. This is the cosine and sine, but this is the complex value representation. So you should believe me that this is the same equation, but with different interpretation. Without approximation. So this is the nonlinear model. So in this case, again, I have 4 groups of estimators. So I have here 4 colors. The new estimator, the GSP weighted widely linear estimator, is the green line. Okay, so you can see that it is the best for small training set if I don't have enough data set. But of course, the widely linear, which includes it will have lower MSE. Okay. If I have enough measurements. And the linear estimators are not so good for this case, okay? And again, if I have changes in the topology, in this case, our estimator outperforms all the other, and this is what you can see here. So the MSE, for example, here you can see that the sample widely linear MSE estimator is not very good estimator if you have added edges, okay? So I say that I don't have much time, so I will skip the nonlinear GSP estimation, but we have also iterative approach of computing the GSP map, and I will move to the Kalman filter. I hope, oh, it works. Okay, so Kalman filter is for tracking of graph signals. So now let's assume that I'm trying to recover X, but X is a dynamic value. And in this case, I have my X as this recursive formulation, but I also have observation, and I have for each time I have different observations. Okay, so this is the same problem because we try to recover X from Y, but now we have this dynamic. Okay, so what we did here, and I say that I don't have much time, so I will try to explain the high level situation. So in this case, we have highly nonlinear situation. We cannot use the Kalman filter. The Kalman filter is the optimal solution if everything is linear, Gaussian, and nice. But if it is not, we cannot use the Kalman filter. What we can do is the extended Kalman filter. The extended Kalman filter is based on linearization of this model. Okay, so this is the extended Kalman filter, and we have the Kalman gain. So the main idea here is, and again, I'm doing it super fast. The main idea here is to work with the graph frequency domain and to use a diagonal graph filter as the Kalman gain. Okay, this is the idea of the GSP EKF. So I'm using the external Kalman filter, and the GSP idea is first working in the graph frequency domain. Second, use a diagonal Kalman gain. Diagonal meaning diagonal Kalman gain as a graph filter. Okay. Now, of course, it reduces the complexity, and we have some optimality conditions. But what is nice is that, and again, I'm doing it super fast. It has some good results if there are mismatches. But what we did now is that, okay, in general, our new GSP EKF has lower computational complexity. It is very good for band-limited graph signals. It has some conditions for coincidence with the EKF. And we have very nice simulations. But in practice, if you think about that, first of all, the graph may be misspecified. So we don't always know in advance that there is a disconnected edge, but we still need to be able to track the signal. Okay, so our topology that is represented by the Laplacian may be misspecified. The noise distribution are usually unknown in practical applications. And also our measurement functions in this case are not necessarily known. So in this case, we know the measurement function, but the state evolution function is not necessarily known. Okay, so what we did here is that inspired by the Kalman-net approach, which replaces the Kalman game with a learning approach, here we propose to use our approach of the graph of the GSP. So you see here the V transpose, you see here that we are going to work in the frequency domain, everything with the tilde here is in the graph frequency domain. And then we learn the Kalman game and use it diagonalized version. Okay, so the idea here is GSP Kalman-net. So we integrate again, you know, I cannot give a seminar today without any deep learning part in it. So here we have this deep learning part is to learn the Kalman gate. But again, this is not end-to-end learning. Instead of taking everything as a black box and trying to use learning for everything, we know that Kalman filter works pretty well. We just want to replace a few things and to learn this Kalman game without that maybe more adaptive to, for example, topology changes. And that's what we saw in the, again, the idea is that if we look on the EKF, the original EKF, it cannot handle with large systems. It cannot work with if the graph topology is misspecified or unknown noise distribution. Okay. At the beginning, we suggested a GSP EKF, but still the GSP EKF works very well with large networks and also with misspecified Laplacian, but it cannot work with unknown distribution or with mismatches. And then we have our GSP Kalman-net that can handle all this situation and has a very small complexity. Okay, so this is the advantage of the proposed GSP Kalman-net. This is on arXiv from last week. So I think Marius is already trying to stop me. So you will have to believe me that we outperform all the other methods. Marius, I think I will go to the conclusion. So to conclude, of course, I didn't have much time for all the things that I planned to, but we propose here different solutions for estimation of graph signals. I hope I convinced you that there is a point in using the graph properties and not just the conventional Bayesian approaches. We have the GSP-based estimators. We started with a simple linear estimator that has a graph filter structure. Then we extended it to the complex value case, to the nonlinear iterative implementation by the GSP map. This is an extension of the maximum posterior estimator. Again, everything is for the same problem, just with slight modifications. Then the GSP EKF with its extension to the Kalman-net with integrating RNN and learning of the Kalman game. I didn't have time to explain about the GSP-based generative and discriminative learning of graph signals, and we have partial domain knowledge. The idea is that if we have partial domain knowledge, if we have partial statistics, we cannot use all the statistics. In all these cases, utilizing the graph properties has many advantages. It's useful when you don't have enough data, when you have mismatches, when you need to save your computational efforts. It is more robust to topology changes and misspecification, and we have local distributed implementations. Our ongoing work is integration into the GNN, graph neural networks, development of performance bounds, and methods with unknown topology that needs to learn also the Laplacian topology. So thank you for listening. Sorry for going after a time. And these are my collaborators, my students that worked on this. I have other students, but these are the students that contribute to the graph signal processing: Ariel, Gal, Lital, Morat, Shlomit, Yaakov, Guy, Annie, and Itai, and many collaborators. So thank you very much.
Yeah, thank you, Tirza, for this great talk. You fully convinced me that this is useful.
Thank you.
So we have some time for questions. You can actually raise your hand. I can give you permission to speak, but we also have some questions in the chat. So Tirza,
So I think that the two first questions, I think I already answered.
Yeah.
And then we have questions about the control theory. So I think, yes, I think, I don't know.
So the question is, can these concepts pave way to apply control theory concepts on graph filters?
So the Kalman filter is used both in signal processing community and in control theory community. So of course we can use concepts like Kalmanet, or in this case GSP Kalmanet, to control. I truly believe that control over graphs is a great idea. I think also there are new methods that try to do Bayesian learning, which is, again, this is not my field, but Bayesian learning of parameters that are based on Kalman filters. So in this case, also to integrate the graph structure in cases, of course, that we have this structure. Okay, this structure can be used and can improve. So yeah, this is a great idea about control theory. I think, yeah.
So there's also another question.
I just wanted to say that in the context of graph, you can also use the statistical graph. So sometimes I have statistical connection between elements. This is also a graph, if you are familiar with graphical lasso. I didn't have time to present it, but this is also, so control theory, maybe it can be based also on the statistics between the different elements.
Okay. So there's another question. In case where the graph is dynamic, can you also consider tracking the graph while tracking the graph signal?
Yeah, this is a great question, because I have the answer for that. That's I hope you are going to come to our ICAS presentation this year. It's still, we didn't get the answer, so we hope to be accepted. But this is exactly the topic of our recent ICAS paper, and I can send it to you. If you email me, I will share with you the ICAS submission. I think the results are next week. But yes, we consider that each time that I presented it, this was the question about how to track the graph itself, not just the graph signals. And yeah, this is a very great question. We have a method. The theory still need to be established, because there is a lot to do there.
Okay. So are there further questions? So I have a question. So in this context where you use the Kramer-Rao bound to select the nodes, so how did you choose your statistic? Which assumptions did you make?
So in this case, we used a Gaussian case.
For the noise, yeah, but for the signal?
For the noise. For theta, no, I don't assume any statistics. So theta is deterministic. This is a deterministic approach. Okay. But the trick here is to use the biased version of the Kramer-Rao bound, because regularized estimators are biased. Okay, we added this regularization, we add bias. So we need to use the biased version of the Kramer-Rao bound, and this was the trick. And then it fits the specific regularization term. So this is the functions. So you need to know, this is the point here. You need to know in advance what is the estimator that you are going to use. Then you can set the sensors. You don't know theta, of course. You don't know the states, but you know the estimator that you are going to, the function that you are going to use.
Okay, thank you. So any further questions from the audience? Yeah, and meanwhile, I have another question. So you were saying that, I mean, you know how to generate data because you have the model, the nonlinear model. So why did you say that you have to use low data? You can generate as much data as you want, or?
Okay, so first of all, thank you. So first of all, there are different problems. So in the problem I considered at the beginning, yeah, I know the structure, but it's not necessary. It's not always the case. So sometimes I really need to use the data, and I want to keep it general. And second, the system is changed. So I cannot work with very large data, and then the system is not stationary. If you think about the electrical network, there are changes all the time, natural changes, good changes, that's okay. But still, you cannot use very large data for each time that you just have a new, I don't know, switch on or off, and you need to generate a lot of data just to handle this situation.
Okay.
But yeah, I agree. Sometimes you have enough data, and the question is not about data, it's about the adaptivity, robustness to your assumptions and things like that.
Thank you. Yeah. So there's a question in the chat again. How did you choose the order of the ARMA model? Did you use a trial and error method or AIC?
Yeah, we use trial and error. You can use also model order selection criteria like MDL, AIC, and things like that. But actually, we were surprised that 8 coefficients are enough to determine this. It was more than 100 eigenvalues, and it is enough to set these 8 coefficients. We tested also other graph filters, not just the ARMA. But from our experience, ARMA was the best, the graph ARMA, which maybe I should give credit to the people that invented it. It's not our work, just to show their work. I think they have a great paper about this ARMA filter. Sorry for going all the way. So from our experience, it was the best filter. So you see here is Sophie, Lucas, Simonato, and Lewis. And this filter, the only thing is that this filter is not local in the vertex domain, but I didn't get into it. But if you want to have local filters, then you need also to only to use this upper nominator graph filter, which is may give higher MSE in this case.
So yeah, another question from my side. So you mentioned that you have a stability issue sometimes. Can you comment on this? So why do you have this? Can you?
Okay. So first of all, in some cases, the eigenvalues can be close to each other. Okay. In this case, we need, if I assume a graph filter, then the frequency response of an eigenvalue should be the same if the eigenvalues are the same or close. That's one point. Another point is that if you use the inverse term, then you should be the regularization term can help, because then the inverse is easier to compute.
Okay. Yeah. So okay. So I don't see any. Okay.
There are new questions. I don't know.
No, I didn't see any.
Okay. You asked me. Okay. Okay.
I think that's. Yeah.
Okay.
So the slides and recordings will be on the EURASIP. I mean, the recordings will be on the EURASIP YouTube channel. Yeah. Can you also share the slides?
I think, yeah. I don't know if you have the opportunity you have this option in the website. So yes.
I think in the YouTube.
Sure. If not, people can email me again, even also with questions or anything. Feel free.
Okay, I think that were all the questions. So let us conclude this session. Thank you very much, Tirza, for giving this great talk today. And thank everybody for attending the webinar.
Okay, thank you very much.
Yeah.
Thank you.
Goodbye.
Thank you, Marius. Goodbye.